Alright, this is my constant velocity lab report for Physics 2211. My name is Rick Lee. For introduction, first, what is our goal with this lab here? It is to compare theoretical motion of an object with a constant velocity to its actual observed motion in the real world. What models and principles will we use here? Well, they include position versus time graphs, Newton's second law of motion, and also the momentum principle. And what will happen in this experiment is basically as no net forces are involved here, the observed motion will basically mirror the predicted motion very closely with a few hiccups here and there from human error. Some physical ideas here that we use here include, by definition, constant velocity means there is zero acceleration, and also if there's no acceleration, there also must be no net force acting upon the system because F net equals ma per Newton's second law, and if a is zero, then F net is also zero by default. Alternatively, the momentum principle can be used to show that there is zero net force as well. Since F net is the derivative of momentum with respect to time, which equals m delta v here is zero because there's no net change in velocity, and therefore that is zero, so F net is also zero because of that. For experiment details, the position versus time graph is chosen because it's easy for readability, and also for Newton's second law and the momentum principle are used because we know certain constants used in these equations, like for example, mass, velocity, acceleration. We want to find F net using these two physics laws pretty easily. We assume here that the cart experiences no friction or net force, despite the actuality of friction and air resistance in the real world. The system is the cart by itself, and the surroundings include the metal track, the table, which is shown in the image here, my hand to push it, and also the air. The initial conditions include the front of the car is placed 60 centimeters along the 200 centimeter track, and my initial nudge gives constant velocity of about 0.77 meters per second, and all else stays pretty constant. After cart starts moving, the group member will record the movement using their iPhone camera until the cart reaches the end of the track and collides with the barricade, which indicates they crossed the entire length of the track. As for the coding implementation, to predict the car's motion, I use GlowScript in Python to construct a line graph that simulates the path of a constant velocity, and the link is right here if you want to see more details. I have my code here, for example, I have the fnet vector is a zero vector because there is no net force at all with constant velocity, and also an initial velocity here of ball.vel equals vector of 0.777 in the x direction for velocity, yes, and also here's the graph of the motion. Also, for the differences between the two graphs, as there is no net force, the velocity is constant across the entire graph for either one, resulting in linear shapes that appear very similar, as you can see right here. And also, the observed graph experiences, well, the blue graph has a slight drop near the end because of friction in the actual world on the system, causing a unbalanced force and thus non-zero acceleration, which slows the velocity down a bit. For possible errors in our experiments, they include the observed graph is always below the predicted graph because the tracker video wasn't calibrated that well. For example, the distance x was 1.6999 centimeters instead of the actual length of 1.84 because of the program. And also, if the table was angled a bit above or below the horizontal, there would have been a net force that caused acceleration and therefore messed with our notion of constant velocity. And the video tracker was also not fully cropped out, because therefore there were some moments in the video where the car was fully stationary or not moving when it should have been actually cruising along already. So here is why the blue graph is below the red graph and also has a bit of like some dips here and there. Now for questions about hypotheticals here. If the orientation of the axis would flip so that the positive x-axis became the negative x-axis, what would happen then? In that case, the observed position would always be decreased because it's moving negative x direction, so that it is always below the x-axis on the position for its time graph, and therefore it is not in the same intended direction as our actual predicted graph from our model. So that would be very bad. And can I determine the actual force count that combine to create a net force of zero? You can estimate there are about 3 forces in total, which include initial push, the friction, and also air resistance. But it's hard to actually know the exact number of forces because there are very subtle forces that include force due to gravity and other forces in the real world, like air resistance, that you can't really account for directly. So it's hard to really pinpoint that number. For my conclusion, as long as there are no unbalanced forces acting on a system, one can accurately predict the one-dimensional motion of an object within a small margin of error using technology. It is hard to replicate a system moving at constant velocity in the real world because you need a vacuum to actually remove things like gravity and friction and air resistance, but most approximations, like the one here, are pretty darn close, I would say. And lastly, computer models are very helpful for tools for modeling physical movement. If you already know things, certain constants like the net force, initial velocity, and acceleration, you can just like plug those values into the computer program, and then it will calculate for you values like um, the the motion of the graph of the object. And that is all for today. Thank you very much and have a great day. Toodles.